highlighting. I'm sorry for this one. Yeah. I was just like circles over here. Ow. Ow.
I never ate it at all. I just
No, actually, I did highlight. I highlighted with one color.
Yo, you've made it. You should be proud of the progress now. We've made it so far through so much calculus now. Too late. No, I'm just kidding. It's actually not, but you don't want to do that.
y'all better wait.
I don't know.
I don't want to watch the boys.
I kind of want to watch it. Y'all play on Friday. Are you not tonight? I wouldn't go.
You introduce this to where.
Yes, I have.
All right. Let's say I don't even know what y'all. My brain is going in. Should I introduce this? I'm just.
Honestly,
I'm looking at y'all, but all I heard
was.
was the word Mormon, and that's all I heard. All right. I haven't told anything yet.
Yeah, but after grade.
Oh no, you'll be surprised. This will stick with you. If I graph something like, let's say you walk at a steady rate. And let's say you are walking I don't know, let's say 2 miles per hour. And I know that this is I understand you could do this a different way, but y'all just stay with me, okay? To find out, let's see. Let's graph this first. Let's just graph if you walked for 2 miles per hour, right? After 0 hours, you've gone 0 miles. After 1, you've gone 2, because essentially this would be a line with a slope of 2. Do you agree? I hope I'm not making this overly complicated. I feel like I am. If I wanted to know, without having like the equation or knowing anything else, but if I wanted to know how far I'd walk over, like, let's say 2 hours, right, without plugging in, you would normally plug in. But let's say I didn't have that. What I can do is I can say from 0 to 2, I can look at the area that's under that. I call it a curve, even though it's a straight line. But area under a curve goes from the graph of whatever it is you're looking at down to the x-axis. So it would be all of this would be the area under the curve. Okay. So looking at this, this has got a specific shape to it, right? Very easy to find the area of that red shape. What would be the area? 1/2 base times height. So I'm spanning 2, and I'm going up how many? 4? 4, it should be 4. If I'm walking 2 miles per hour, right? So over the course of 2 hours, 1/2, 4 times 2, or 2 times 4, whichever way you want to go, and I would get, what's that give you? 4 miles. Okay. Now look at the difference here. I've gone from miles per hour down to miles. What have I essentially done? Kind of like related, right? Antiderivative. That's exactly what I'm doing. To get from miles to miles per hour, I'm thinking about derivative because I'm thinking about a rate. So I'm going backwards. And that's kind of the relationship here. And we've hinted around at that a lot, that the area under the curve is actually the antiderivative. We call it an integral. But we can find the area of the curve. The easiest way is if we can get it into a shape that we know to find that area under. Again, only going to the x-axis is where it stops. Okay, so if we can get a geometric shape, we'll review things like area of a trapezoid, which, by the way, how do you find the area of a trapezoid? 1/2. Add the 2, but do you know what a trapezoid is? Yes, I should. Okay. The woo. Okay. 2 sets of parallel sides. It's a type of parallelogram, yes. Base 1, base 2, yeah, it's kind of like a rectangle and a square kind of thing. And here's your height. Drop down at 90 degrees. We will use that a lot. We will use rectangles a whole lot. I hope you can do the area of a rectangle. It comes with, right? What other shape will we use? That's probably what we'll stick with, but you'll see lots of triangles if we're talking about geometric shapes. 1/2 base times height, very similar to the trapezoid. You might see a circle. These are just ones that they kind of assume you know. I told you they'd give you all the equations, but these ones are kind of assumed. What's the area of a circle? Come on, y'all. What's the area of a circle? Pi r squared. What if 2 pi r would be the circumference? What if it's a semicircle? Divide by 2. I think those are all the most common ones that you will see as far as area under the circle. So, area under the curve, excuse me. Let's do a general example, and then I'll show you one where we have to actually divide it up. Let's see here. Consider a snowstorm that starts at 3 a.m. I'm pulling this from your book because I can't come. No, I love snow. I wish it would snow here. Did it? Over the first 2 hours, the rate of snowfall increases from 0 to 1.2 inches per hour at 3 a.m. first 2 hours. So 3 to 5. For the next 3 hours, it continues to fall at 1.2 inches per hour. So for the next 3 hours, so now I'm from what? 5 to 8. Steady at 1.2 inches per hour. At 8 a.m., it begins to taper off, decreasing at a steady rate from 8 to 10:30, by the way. Decreasing at a steady rate until the snowstorm ends at 10:30 a.m. Decreases until it stops. Find the total amount of snow that fell over the course of the snowstorm.
What is your
Okay, so that's saying that the rate, right? The rate of snow from 0 to 1.2. So here's the way I'm gonna think about it. It is slope, but I'm graphing the slope. I'm not graphing like, this is a little different, let me show you. I'm gonna graph the rate on the y-axis, and my x is still gonna be my hours. X is always your time, yeah. And I'm gonna make this actually go, we'll just start it at 3 a.m. And I'm gonna go every hour. So there's 4, 5, 6, 7, 8, 9, 10, 11. There's 11 a.m. All right, so from 3 a.m. until what time? 5, 3, 4, 5. It went from 0, and if this is my rate in inches, my rate's coming in inches per hour. So I'm going from 0, and then at 5, it goes up to 1.2. So I'm going to say this is 1, this is 2 inches per hour, so just a little past 1. So about right here, right? That rate is increasing. I'm going to assume it's a steady increase, just like I was walking at that same speed. I'm going to assume that it's increasing at a steady speed. Then from 5 to 8, it continued to fall at 1.2. You won't have to draw a lot of these. Most of the time this is given to you. It is. And then it stops at 10:30 as it steady goes down. So I've got this constant. So you're right, it's a trapezoid. I could also look at it as two triangles and a rectangle, but I would probably look at it as a trapezoid. So if I want to know how, well, sometimes if you forget how to find the area of a trapezoid, you could always do two triangles and a rectangle and add them together. It's the same equation. Yeah, that's definitely something I would do. I would divide out and go, okay, here's a square, here's a triangle, here's a triangle, here's a rectangle. I'll just do boom, 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 and add them together if I forgot. But you can do whatever. All right. Well, let's figure it out, right? Let's see. The total amount of snow fallen, I need the area under the curve. So I'm just going to break this into shapes. What's base 1?
7.5.
Or 3.
It doesn't matter which one. Oops. Yes. What's the height? And I'll show you where I got them from. It goes, this is, 7.5. This is 3, and it goes up 1.2. So how much snow fell during that time? 6.3 inches. Yep. That's pretty easy, right? It's pretty easy, especially if you're given the graph and you can look at it 9 times out of 10, you will be given the graph. You're not going to have to interpret a problem quite like that, like we just did. And you might have a couple that you have geometric shapes, but a lot of the times it's not. So let me show you what we do. What if I had something like, back to particle motion, that's Stella's favorite. Let's just say that my velocity was modeled by t squared. We'll keep it easy. If I find the area under the curve here, what am I finding? Antiderivative position, so how far, the total distance that I went, right? Does that make sense? If I do the area under velocity, then I'm talking about, right. All right, so if I graph this, I end up with something like, okay, no, not total distance. It's not going to be my total distance. It's going to be where I end up. I have to think about it a minute. Area under is where you end up. It is the position at that point. Right. Why am I only doing that side of that parabola? Positive, because I can't have negative time, right? Now here's the problem. Let's say I asked you, where is my bug at 3 seconds? It's curved. We don't know how to do that, right? Why? That's velocity. I need position. The area under this curve, this velocity curve, is where I end up on position. Okay, but remember whenever we do an antiderivative, I end up with that plus c. And we don't know any other points. So here's what we have to do. We have to think about, you're right, this point would be 3, 9, because this curve is x squared. But I have to think about the area under this curve. Well, now I'm in a bit of a pickle because it's curved, right? There's not a shape that I know. So here's what we do. Okay, here's where it gets real, and this comes up. This is guaranteed question, so we'll spend probably 2 to 3 days on this particular concept. All right, what we do to estimate the area under the curve is we break it into shapes that we know. The one that we use the most, we use trapezoid, sometimes we'll get to that later. The one we use the most, that is the most common, is rectangles, okay? In other words, let's say I told you to partition this into 3 different rectangles. I'm going to call that N. That's how many rectangles I'm going to use. And here's what I'm going to do. I'm going to take each rectangle. If I'm dividing this into 3, then here's 1, here's 2, here's 3. Do you agree? I'm going to make it a rectangle. Just wait just a second. All right, here's what I'm going to do. I'm going to go, and there's 3 ways we can do this, okay? We can go from the left end of the rectangle, we can go from the right end of the rectangle, or we can go in the middle. We're going to start with in the middle because it's the most accurate estimate right now for us, okay? So we're going to find the middle of this interval, and we're going to find where that falls on my curve. So halfway in between 1 and 0 is what? 1/2, right? We're going to find where that is on the curve, and we're just going to make a rectangle out of it. Okay? Now notice I'm going to be missing, here's my curve, right? I'm going to be missing a little bit here. Actually, I'm going to be missing a little bit, and I'm going to be gaining a little bit. But because I went right in the middle, it's going to kind of work itself out, right? So here's rectangle number 1. So rectangle number 1, and it won't take this much work to do every single one. They'll start to pop out at you, and you'll see. Rectangle number 1 is going to have a width. They're all going to have the same width, in fact, right? Because I made sure they were equal intervals. It's going to have a width of 1. And what's the height? 1/2. Because where did I go up? Oh, no, the height's not 1/2. I'm sorry. What is the height? What's the curve? The curve is x squared. 1/4. 1/2 squared. Because to find this point, I have to plug into that function, right? Is this making sense to you? Do you see how I'm finding it? All the width is, okay, the height is coming in on the curve itself. So every height is going to be f of the midpoint. And f is x squared, because I'm actually going to be on that curve, right? I messed y'all up because I just wrote 1/2 to start with. Okay. Okay. So the area of rectangle number 1 would be what? 1/4, because it's 1 times 1/4. All right, look at rectangle number 2. Again, my width is going to be 1. It's always going to be 1. I made sure they were equal intervals. What's halfway in between 1 and 2? 1.5, 3/2, 1.5, any of those work? What is my height going to be? This point is 3/2, 9/4. That's my height, right? So this rectangle looks like this. Do you see how, I don't know why that thing keeps popping up. Do you see how I am still missing some, but yet gaining a little bit extra here, okay? So my height here, so what's the area of rectangle number 2? Okay, try rectangle number 3, see what you get. That's a 9. Yep. Here, well, it is just because the width is 1 each time. If the width was 2, then the area would be twice the height. Because remember, it's a rectangle, so it's like, yeah. Y'all okay? 25/4 for that third rectangle. So now, if I want to estimate the area under the curve, and again, this is just an estimate because it's not exact. Remember, I got a little bit more and a little bit less, and depending on the curve that I'm looking at, it's going to be a little bit different. But what's a good estimate for the area under the curve here? You add all those together, right? So an approximate area from 0 to 3 would be 35/4. So where is 8.75? Where is my bug at 3 seconds? Approximately. So S of 3 is approximately 8. Yeah, because I said between 0 and 3. What would happen if I added more rectangles? Like, what if I said, okay, I want you to find the area under the curve using 6 partitions instead of 3. What do you think is going to happen? But what's going to happen with my area? You think it's going to get bigger? You tell me. I don't know. What would happen if I
just add all those together?
Let me ask you this. I'm still finding the same thing, but I've got twice as many rectangles now, right? So now, instead of this being one big rectangle, I've got this, this, and this, and then I've got twice as many, right? What happens as I increase the number of rectangles is what I'm asking. It gets more specific. I get more accurate. Do you agree? The more partitions I cut it in, the closer I get to the actual area, because essentially if I could just make this teeny little sliver of a rectangle, right, then I'm going to be more accurate as I go because I got less space to lose or gain, right? Does that make sense to everybody? Yeah. So the bigger the N, the better it is. Now, they tell you how many. They tell you, yes. And so when they give you that N, right, you have to find that width. Your width is going to be your highest you go to minus your lowest divided by how many intervals you need. That's going to give you the width of each rectangle, right? 3 minus 0 divided by 3 is 1. That told me my width of each rectangle was 1. Does that make sense? And so I could really simplify this whole equation down a little bit because I've got to have the same width. I'm going to do equal rectangles, right? To say that my area under that curve is going to be whatever my width is times, and then each of these, if you look, what really am I doing? I'm just finding f of each midpoint. So midpoint 1, midpoint 2, until I get to that very last midpoint. Does that make sense?
How do you define it? Add all those areas together?
Yep. And I kind of factored out that width so I didn't have to do it each time. Is all I did, right? Because the width is going to be the same on all of them because they're all the same. So it's width times height, width times height, width times height. Instead of doing that each time, I just add all the heights together and times by the width. Does that make sense? It just makes your life a little easier. You don't have to do it that way. That's just the way. No. Mm-mm. You'll divide to find your width of each rectangle, yes. Okay. Now, this is midpoint. It's the hardest, in my opinion. This is what we call, by the way, RAM, which stands for rectangular approximation method.
So what was the final answer? Like the final answer?
Yeah, 8.75. And this one in particular is MRAM because it uses the midpoint. It's midpoint RAM. There are two other types of RAMs that I'm just going to show you, and I'm almost done. I promise I'm almost done because I really just wanted to introduce this today and get your feet wet with it. All right, so this is midpoint because it uses the midpoint, right? It uses the middle of your interval. Your calculator, by the way, uses this method with an infinite. You know how we do limits where h approaches 0? Okay. When we find area under a curve, we're letting n approach infinity. So we're trying to get an infinite number of little rectangles under there so that we can get the area. That's how it works. Okay. Just for your knowledge. You don't have to know that right now. All right. That was MRAM. What happens if I change? Notice my little triangles over here, and my rectangles. I'm going to draw the same curve going to 3. And I'm going to do the same 3 partitions. Make it easy. We also have what we call right RAM. I'm going to draw this in red so you can see. Right RAM says start at the right end of your interval and let that be the height of your rectangle. So the right end of your width is your height for that particular rectangle. So here's my height, and it goes over like this. Notice all this extra space I'm gaining when I do this, right? Starts here, it goes all the way over to the end of the interval. It starts here, it goes all the way over to the end of the interval. Using right RAM on a curve that is concave up like that is going to give me too much area. Do you see that? It's an overestimate, but it's an estimate nonetheless. That's why MRAM was the best. But different curves call for different things. Okay, so in this case, each height, my width is still 1, right? But instead of having to calculate the midpoint here, it gives me a little more, it's a little easier to find in my opinion because you've got these whole, you don't have to find the middle and then plug it in. We'll just find f of 1, f of 2, and f of 3. We don't do anything with f of 0 because we're using the right endpoints. Then we have left RAM. And left RAM uses the left endpoint to give your height. Notice whenever I start, I don't even have a rectangle, right? Remember, I'm always going up to the curve on the left. But this one, when I'm concave up, gives me a what? It leaves out a bunch, right? Leaves out a whole lot. So now, all right, this black is the actual area under the curve. Now I'm in blue here. And I've got a lot that's left out, right? Actually, that last blue shit. All of this is left out. All of Where am I now? All of this is left out. All of this is left out. So it gives me an underestimate.